Geology is the study of rocks and deals with a special kind of science which allows one to delve into the deeper aspects of the system around which Earth works. Mathematics is a subject that helps you to calculate and come to logical conclusions. It is interesting to note that geology and mathematics are interrelated and are a part of the same coin. Now, one would wonder how this is possible. To put it simply, mathematics is a useful subject for geologists. Mathematical geology is a subject that helps in making models, formulating them, and is proving to be useful during scientific theories and geological phenomena. Geomagnetic fields are in fact used in navigation, oil production, geophysical surveys, and in various scientific studies ranging from the topmost part of the atmosphere to the deepest interior portions of the Earth. With geologists working in a different kind of setting, the environmental companies and other organizations are trying to cement this link between geology and mathematics. Geology is a subject based mainly on calculations of the position of the Earth's crust and a compounded result of many occurrences in Earth. This chapter would deal with such aspects and more in detail. Development of geology and its connection to mathematics. Application of statistics and other forms of mathematical identities to geological work mainly depends on the data obtained from nature. The occurrence data of many fossils below the Earth are first analyzed. This is done with the help of fixed statistical rules, and there are stratigraphic techniques specially meant for this. These are a part of the system. For example, the permutation of the score matrix is an important part of finding geological information. With the help of such calculations, the optimum sequence is obtained. Fossil distances. Geologists usually calculate the distance between fossils and facilitate the automated biostratigraphic zonation as the chronological correlation with the right kind of calculation. There is uncertainty in every trial. This is also looked into and it is accordingly quantified. When all the important rules are met with, the stereographic study is ready to be declared, and the results of such studies help to find out the solutions to the problems that are involved with allocating fossil events. Statistics and geology. The early years have seen a continuous correlation between statistics and geology, and this is done mainly with the need for dealing with a host of biological data that is given. Geology has contributed not only in application of the data, but also in gaining more knowledge of the conditions. Thus, the best thing that has happened now is the introduction of geostatistics, which helps people to know about a new kind of statistics which has variables and which helps in quantifying stratigraphic methods. These techniques have all been applied and reapplied, tested and retested, and finally has come to this conclusion that there is a link between geology and statistics. Quantitative stratigraphy. Quantitative stratigraphy is a field in geology which deals with the mathematics of geology. It helps in applying the numerical and statistical methods for the benefit of geology. When there is a sedimentary basin, for example, then there are sediments which fill the gap. The total thickness of this basin is measured and the stratigraphic data is drawn accordingly. There was a requirement to have modern technology help to perform a perfect synthesis of the existing data. Quantitative stratigraphy synthesizes a huge quantity of fossil data, which is again based on statistical and mathematical rules. There are certain steps to follow for introducing stratigraphic data, to the analysis of data towards understanding how stratigraphy occurs. The first step for introducing such data is called an event. A biostratigraphic event is defined as a particular stage in an evolution which is located in a unique position in the time context. When this definition is done, then the order of events has to be represented in the right sequence. This is where the mathematical information is necessary. Once you have defined the order of event, then the entire thing falls in place. Mathematics as an approximation to reality. Geology is frequently regarded as a qualitative, that is, descriptive science. Geological discussions often revolve around questions about what happened and in what order. For example, when was a particular area under the sea deposited with sedimentary rock, and does the erosive surface at the top imply that uplift above sea level occurs subsequently? However, the same geological information can be described quantitatively, that is by numbers. Geology is also concerned with the influence of one process upon another. How does changing water depth affect sediment type? Once again, it is possible to do this quantitatively by producing equations relating, say, grain size to water depth, unlikely to be very accurate, but in principle possible. This figure illustrates a situation in which a quantitative description can be attempted. It shows a lake within which sediment suspended in water rains down and slowly builds up on the lake floor. Obviously, early deposits will be covered by later ones. This results in a relationship between depth below lake bed and time since deposition. The deeper you go, the older the sediments get. Now, if the rate at which sediments settle upon the floor is approximately constant, sediments buried 2 meters below the lake bed are twice as old as sediments buried by 1 meter, and sediments buried by 3 meters are 3 times as old, and so on. Thus, if you double depth, you double age. If you triple depth, you triple the age, and so on. This can be expressed mathematically by the equation age is equal to k into depth, equation 1.1, where k is a constant. Constants are values which do not change with a given problem. The period symbol dot is often used in place of x to indicate multiplication, and so equation 1.1 reads age equals k multiplied by depth, which can equally be written in the form age is equal to k into depth, equation 1.1, or age is equal to k depth, equation 1.1. All of these different forms for equation 1.1 simply indicates that the age of sediment equals its depth multiplied by a constant. This constant tells us how rapidly sediments accumulate. A large value for k implies that age increases very rapidly as depth increases, that is, sediments accumulated very slowly. A low value implies that the age increases more slowly, that is, sediments accumulated more rapidly. In a particular lake, it might take 1500 years for each meter of sediment to accumulate. In this case, k is equal to 1500 years per meter. With a lower sedimentation rate of say 3000 years per meter, would have a more rapid increase in age with depth of burial. Application of statistics to geology. Statistics is an important part of mathematics, but it is equally a very important part of geology too. Geology differs from the experimental sciences in that most geological data are fragmentary and are derived from the surface manifestations of natural processes that are uncontrolled by the geologist. So, geologists must make do with the data available, which are seldom those with which they would prefer to work with. It is here that statistics may enable them to plan data collection and deduce inferences that are not readily distinct from the raw fragmentary observations collected. Many of the difficulties in statistical analysis of geological data stem from the data sources. In geology, most data are obtained either from uncontrolled natural processes such as volcanic gases and earthquakes, or more often from the results of events concluded in the geological past, for instance, from basalt flows and granitized rocks. In principle, numerical data for examples of analysis are available from most, if not all, fields of geology. Numerical data are common in hydrology and in special studies in paleontology and geomorphology. From sedimentology comes data on size and shape characteristics of particles. There are many data in petroleum geology. Petrology furnishes many data, although those potentially most interesting are rock analysis, difficult to compare because of marked inconsistencies from one laboratory to another. Out of the various statistical applications in geology mentioned above, we will try to understand how histograms can be used in geological data analysis. It is easier to look at a picture than to read a table. It is generally useful to draw a histogram to represent the frequency table pictorially. This table illustrates the frequency distribution of 224 phosphate assays. Here is a histogram of the phosphate data. The diagram is made by plotting a series of contiguous rectangles whose base length corresponds to the interval width from the frequency table and whose height corresponds to the number of observations in each interval. This was an example of where statistics is used in geology. In addition, probability calculations and statistical principles of sampling are other widely used applications of statistics in geology. Trigonometry and geology. How steep is this hillside and will it fail? How high is that mountain? These sorts of questions pop up all over in geosciences, from plate tectonics to maps to ocean waves, and they require you to find either an angle or a distance. To do this, we often use trigonometry, which is much easier when a right angle triangle is involved. An understanding of angles and the ability to manipulate trigonometric expressions is essential for a geoscience student. Geoscientists use both of these concepts in numerous applications, from coastal geology to mineralogy to geologic mapping. Trigonometry and angles are used in a wide variety of geoscience topics, including waves refracting as they approach shore, geologic structures and mapping, compass direction, strike and dip, ocean and seismic waves, dunes and wind direction, subduction zones, slope stability, planetary applications, that is parallax. Because everyone has different ways of learning, mathematicians have defined a number of ways that quantitative concepts can be represented to individual students. Below are some ways that angles and the relationship to trigonometry are used in geoscience concepts. Graphical or visual representation. Commonly, students will have encountered angles in degrees, an angle of 90 degrees for example. In mathematics, the coordinate system used to talk about angles is a right-handed coordinate system. 0 and 180 degrees are parallel to horizontal and 90 degrees and 270 degrees are parallel to vertical. Numerical representation or angle units. Geologists and mathematicians often use two different systems to express angular measurements, degrees and radians. As discussed above, geologists and sometimes mathematicians generally use degrees for measurement of angles. A circle has 360 degrees total, a right angle is 90 degrees. Geologists use circle geometry to talk about compass directions, where 0 degrees is at 12 o'clock and angles increase in the clockwise direction. Geoscientists also talk about angles in degrees when we talk about orientation of one line or vector to another. Examples of this include relative plate motions, wave propagation, and slope stability. For these applications, we use triangle geometry to describe these directions. Symbolic representation. Most students will be familiar with the right angle definitions of these functions. Sine, cosine, and tangent are abbreviated with sine, cos, and tan respectively. Sine theta is equal to opposite by hypotenuse. Cos theta is equal to adjacent by hypotenuse, and tan theta is equal to opposite by adjacent, where theta is the angle of interest, opposite, adjacent, and hypotenuse represent sides of the triangle. Example: a geologist can measure the distance d of an outcropping strata and its inclination, which is the angle or how steep the layer is going down. A geologist uses a simple geologist compass, which is always equipped with a clinometer. Yet, measuring that length d of the outcrop doesn't correspond to know the real thickness of the strata, w. So we want to find out what is the real width of the strata. Solution: the real width or thickness of the strata w can be simply derived by field measurements of d using a meter or just by counting the footsteps, and theta using a geologist compass. In fact, trigonometry enshrines secret natural rules which bind those three units w, d, and theta. In other words, we can imagine that d and w are the sides of a right angle and theta is one angle of it. The Greek astronomers found out that the relation which binds those three things, d, w, and theta, in a right triangle is universal, that is, valid in all universe and independent from the size of the triangle. And the relation is sine theta is equal to w by d. Now sine theta is just an intelligent proportion, a number going from 0 to 1. From algebra, you will know that the above relation can also be written as w is equal to d into sine theta. Now, let's say we measure theta is equal to 30 degrees and d is equal to 50 meters. Then we have w is equal to 50 into sine 30. Therefore, w is equal to 50.0, 453990, which is approximately 22,7. So, the solution of our trigonometry in geology example is that the real strata is about 22,7 meters wide. Application of algebra in geology. Algebra is the body of mathematical knowledge that deals with symbols. It deals with constants such as the number e is equal to 2.718 and variables such as x, y that can be coordinates of a point with x and y taking any value. Each value of x and y is a number that can be added, subtracted, multiplied or divided, and hence algebra can be regarded as generalized arithmetic. Algebra is about treating and manipulating numbers as symbols. Various dimensions of algebra, like the concept of Pythagoras theorem, equations for intersecting lines, equations for a plane, and functions are applied in geological calculations. Let us consider an example where algebra can be applied in geological calculations. Example, line joining two points. Let us consider an example wherein, given the coordinates of any 2 points, the parameters of the line that joins them has to be calculated. The rule x minus y into x plus y is equal to x squared plus xy minus xy minus y squared is equal to x squared minus y squared is used on a number of occasions. Consider 2 points AB with coordinates A 1234.56 and 2345.67 and B 1296.32 and 2417.38. Then M1 will be YA minus YB by XA minus XB, which is equal to 2347.38 minus 2417.38 by 1234.56 minus 1296.38, which is equal to minus 71.71 by minus 61.76, which is equal to plus 1.61108. C1 is equal to YA minus M1 XA is equal to 2345.67 minus 1.61108 into 1234.56, or C1 is equal to YB minus M1 XB, which will be equal to 2417.38 minus 1.61108 into 1296.32. In both cases, this gives C1 is equal to 912.21. Hence, the line joining A to B is y is equal to 1.61108x plus 912.21. The relationship y is equal to mx plus c is a general expression for a straight line in rectangular Cartesian coordinates. Y is said to be the dependent variable and x the independent, meaning that for any chosen value of x, we can obtain a unique value of y. Calculus in geology. Calculus involves making calculations of anything that changes, and geology is mostly about changes. You can calculate certain things using straight line equations, but in the real world, nothing is straight line. Let's take a petroleum deposit. You want to know how much, how fast it will fill. How do you figure this out? Well, for answer 1, you could just put a box around it, make an estimate of porosity and give it your best go. Or you can apply a curve to it and make a much better estimate using calculus. Your various tests will indicate changes of porosity over distance as well as an unusual shape of the deposit. You will need calculus to determine what is really there. As for the speed at which you can get the petroleum out, this is determined by pressure, permeability and viscosity of the fluids. Pressure changes over time, and it is highly likely that in your oil reserve you just discovered that permeability changes with depth. Thus, you can have a straight line. For instance, you guess that you can produce 100 barrels per day, or you can have a much more accurate estimate using curves related to permeability and pressure changes over time and distance. Which one will the investor prefer? They would fund the calculus-derived estimate. In the environmental field, we are concerned with pollutants in the ground. But pollutants are never constant. They change over time. How long will this take? To estimate natural attenuation, which means you inject nothing into the ground but monitor the pollution until it cleans itself, you are going to have to use a regression model. And that regression model will not be a straight line, it will be a curve. And to calculate the end of that curve, that is, when the pollutants will clean up on their own without you doing anything, will require calculus. Most of these calculations are done with computers. But you need to understand the concepts and be able to work simple questions. Structural geology uses a lot of calculus. Stress changes over time. When does the rock snap? Also, you'll find that hydrogeology uses a lot of calculus. Water flow changes over changes of permeability, slope and viscosity of fluids. Derivatives of duration. We can plot the time fx that passes as a seismic wave travels through space x. This function is known to many geophysicists as the time to depth function. It is the key for converting borehole measurements effectively recorded using a measuring tape to seismic measurements and recorded using a stopwatch. Now let's take the derivative of fx with respect to x. The result is the slowness function, the reciprocal of interval velocity. The time duration that a seismic wave travels over a small interval, 1 meter. This function is an actual sonic well log. Differentiating once again yields this curious spiky function. In this example, creating a synthetic seismogram mimics the calculus of geology. Conclusion. It is a known fact that geology and mathematics are related to each other. Whether it is the most feasible way or whether it is the best possible method remains to be seen. Geology and application of statistics, trigonometry, algebra and calculus is very feasible and the best thing to be done in today's continuous changing world. Yet, there are other areas that we should look into and many other problems that we have to sort so that the link is continuous and easily attainable one. Discovering Earth is possible now with the help of simple mathematics and logical conclusions. Analysis of data obtained can now be utilized for the betterment of Earth, and today it is a great way of bringing out a proper conclusion to the perennial supply of geological data that we have. With the dimensions of science and mathematics changing, geology is no longer a subject that is just the study of rocks. It also involves a deeper insight into the values of mathematics as a way of life. Geological conclusions and easily available mathematical logic is what maintains the balance between the two. Truly, this could be a path-breaking combination in future years.